We often view the world through a sharp divide. On one side is biology, warm, organic, and self-sustaining. On the other is the computer, a cold, geometric, synthetic machine. But when we examine these systems through the laws of physics, the boundaries between them become difficult to define. The thesis we're exploring is that the separation between meat and metal is a material variation rather than a physical divide. This chart from the protein and the silicon introduces the dual machine eclogue. It posits that both human biology and modern circuitry arise from a single physical law, nature organizing complexity out of matter. This framework establishes a dual machine reality. It allows us to compare the protein machine of the human body directly against the silicon machine of the computer. In this context, there is no ghost in the machine. Both biological and synthetic bodies are matter organized by nature to solve identical engineering problems. To function in the physical world, every complex system requires a mineral anchor to orient itself. The silicon machine uses quartz crystals. These are mineral oscillators on the circuit board that vibrate at highly precise frequencies, allowing the computer to maintain an internal clock. The protein machine relies on minerals as well. Housed inside the human skull are otoconia, microscopic mountain rocks made of calcium carbonate. In the inner ear, otoconia crystals shift under gravity, allowing the brain to maintain spatial balance. While one tracks gravity and the other time, both machines rely on crystals to provide a steady reference point for internal logic. Despite the appearance of soft flesh, the protein machine is just as dependent on primitive stone components as the silicon board to stay steady. When we move from structure to communication, the comparison becomes even more direct. We can measure the activity of both systems as literal voltage. In a silicon machine, information moves via the high-velocity drift of electrons traveling through a crystal lattice to flip internal switches. The protein machine uses action potentials. These are electrical signals that use ions instead of electrons to generate a charge. This shows the flux of sodium and potassium ions rapidly moving through protein channels to create electrical pulses. This ion flux and electron drift are two material approaches utilizing a single conductive field to propagate information. The human heart and the computer circuit board are the same electrical machine, separated only by their choice of conductive material. At the micro level, signals must navigate gaps in their respective hardware. This visualization shows a DNA helix and silicon chips bridged by a shared electrical discharge. In biology, the electrical signal leaps between gaps along the nerve, called the nodes of Ranvier, a process known as saltatory conduction. In this rendering, biological leaps match the discrete on-off state switches of a logic gate. At the synaptic cleft, the signal transforms into a chemical bridge before reigniting as voltage, organizing the propagation of information just like silicon pathways. The biological machine executes mathematical state switches using wet components, mirroring the operation of a logic gate. From a macro perspective, it appears humanity did not invent the circuit board out of thin air. Through engineering, we have recreated the physical laws that built our own brains, substituting silicon for protein. This mechanical device on a hybrid track illustrates the conclusion. Humans and technology are two different houses built from the same evolutionary components. The protein machine thinks in pulses. The silicon machine thinks in light. These are dialects of the same physical law. The shared foundation between them is the conductive field, where both protein and silicon organize the flow of information.